Good morning, dear professors. We are from Vietnam. My name is Vinh and my friend is Sui. Today I am very happy to present our topic on effect of annealed temperature on the magneto-reactance for series temperate amorphous response using magnetic sensors. First of all, we introduce about our study. The reason why we choose this subject: nanotechnology sensors have superior properties such as high accuracy, smaller size, faster speed, and durability. Many new features are also being exploited when fabricated on nanotechnology platform. In particular, the combination of magnetic sensor technology and nanoscale magnetic materials has opened up a new solution for detecting and treating this cancer. What did another group do? Many groups study on effect-based amorphous response to design new magnetic field GMI sensors, and the sensitive attract is 600 millivolts per state. They measure in a range of very low and very high frequencies. The amorphous in our work, we have demonstrated a novel method of detection nanoparticles by designing a sensing element shell that consists of multiple rounds soft ferromagnetic response theory, and it's called ferromagnetic nanoparticles iron oxide with defined accurate concentration.
I briefly introduce our experimental. The CoFeZrB compound was prepared by fast cooling methods to find the optimal condition by annealing temperature from room temperature to 600 degrees C. Measurement GMI at low frequency 1 to 10 MHz. Superparamagnetic iron oxide nanoparticles were prepared by a chemical method. Detection: we use optimal ribbons annealed at 300 degrees C. Measurements are XRD, TEM, FTER, VSM, and GMI. The main batch is discussed and discussion. Fig 1 shows XRD bottom of as-quenched and annealed ribbons. Ribbons were annealed at different temperature from 100 to 600 degrees C. All samples are amorphous ribbons except the sample was annealed at 600 degrees C. In the curve appears some peak, that means the sample was crystallized. Fig 2 is M8 at 300 K for as-quenched and annealed ribbons. The offset shows magnetized curve of the sample are superparamagnetic. Fig 3 is delta X per X from ribbons at 4 and 6 MHz when increasing annealed temperature from room temperature for 300 degrees C. Delta X per X increase, take a double peak and get the highest volume, but TA equals 600 degrees C, delta X per X nearly zero. Eta 8 for the as-quenched and annealed ribbons at 4 MHz. The field sensitivity of delta X per X as a function of DC magnetic field for the as-quenched and annealed ribbons at F equals 4 MHz. Ribbons was annealed at 300 has highest sensitivity volume about 40% per offset. We found the optimal condition for CoFeZrB compound at TA equals 300 degrees C with highest volume of delta X per X and field sensitivity of delta X per X.
Figure 5. The FTIR spectra of iron oxide ambience. The index is termed IMG for iron oxide. The iron oxide crystal phase is characterized by two FTIR strong bands, shifting mode, and vibration. To understand the absorption mechanism of the oil on the surface of iron oxide nanoparticles, consequently, two peaks were attributed to the asymmetric Ca2 and the asymmetric Ca2 surface, respectively. Term images show that the NBS size about 8 nanometer and evenly distributed. Figure 6. M8 has for iron oxide NBS at 300 K. It shows the absence of remanent magnetization and zero conductivity. M8 mass equals 30 mU per gram. Its delta X per X for the sensing element coiled samples contains nanoparticles iron oxide at the frequency 247 MHz. At a given frequency, there were clear increase in the mx radius with the concentration of the SPIO particles in the range 0 to 6.12 mg. To better prove such changes, we have performed a quantitative analysis of modification on the SX response rate to present of this SPIO nanoparticle at selected frequency of 247 MHz, where their corresponding radius were achieved. However, the radius first increased supply with increase in particle concentration from 0 to 1.92 mg and then remained almost unchanged for higher particles concentration, later or equal 1.92 mg. Figure 8, delta eta CH of element called iron oxide NBS at 7 MHz. Figure 9, delta eta C amps at different HX at frequency 7 MHz. He equals 0 state the delta eta C about 1.3.52%. Hm equal HK, delta eta C about 4%. Hm larger than HK, delta eta C equal 3.1%. Figure 10, delta eta CH at 1.53 state at frequency 3711 MHz. As a result, no further increase in the delta eta C is obtained. Clearly, the concentration of 1.92 mg sets an upper limit of the sensor detection of 8 to 12 nanometer iron oxide nanoparticle. Conclusion: but we have performed a systematic study of the longitudinally excited magneto-reactance effect of an inductive coil with nanoparticles iron oxide in its core. Our result shows that dx per x ratio and field sensitive increase. This result has a practical importance in designing novel magnetic sensors based on the mx effect for sensing application. Furthermore, the sensitivity of SiC were improved when the external magnetic field He reaches proper magnitude. He per equal Hk for the maximum sensitivity of SiC. This is necessary condition to improve sensitivity for ultra-sensitive detection of magnetically labeled cancer cells and biomolecules.